Hello everyone. Let's talk about simple digital input and output in microcontrollers and how to use it in Rust. In previous tutorials I showed you how to toggle simple LEDs, and I was using these structures GPIO C for using an embedded LED to show a value like on and off. However, now I will go through the separate pins that you see. Every MCU has several of them. And I will be covering input and output. Let's get started. This is all the pins in my MCU. I have a Cortex M0 and it has several of them. I will be using PA0 as an example, and we'll get started with output. Output means that I want my device to set either a high or a low value from a pin. So I could in this case control, let's say, PA0, and I can make it either be a 1 or a 0, and this could be used to signal things or to display other values. For simplicity right now I will put an LED and I will say let's connect it to PA0. So I'll put a wire between PA0 and the LED, and because this, when I set this to 1, I want the LED to turn on, so I will add a ground and connect it like this. This is the circuit that I will build on the breadboard, and what I expect is when PA0 turns on, the LED will be on, and when PA0 is off, the LED will turn off. That's it. I placed the LED on the breadboard, so let's code. I will be changing my example, which is the embedded LED. So the embedded LED is on GPIO C. Instead I want to use GPIO A because I want to control PA0, and I convert it into push-pull output. What this means is, one output I can write the 0 and the 1, and push-pull means I can write and I can write 0 or I can write a 1. So 1 is push and 1 is pull. So I can push it to 1 or I can pull it to 0. So I have this delay. Let's put it half a second, and I have the LED toggle, and I will do cargo run, and you notice that the LED toggles on and off. Great. So I have a simple LED and I can toggle it on and off. The next step would be, what happens if I don't want an LED? If I want, let's say, an LED strip, or I want some sort of a light. Let's say I have a sensor, and when I enter my room, my sensor detects that I entered the room, and I want to turn my lights on, or I want to turn a light stand on or something like that. So in this case it's usually larger loads, and there's a limited amount of current that you can drive through this. So what you want instead is to control and make it act as a switch. And there are various ways to do this. One way would be to use relays. They look kind of like this, or better yet, I will show you some Google images of relays. There's either solid state relay. These don't click but are probably a little bit more expensive, and these are the typical relays which you can get in example kits, and they are magnetic. They use an electromagnet, so they have a clicking sound whenever they turn on and off. The other thing that you have to take care about is what is the voltage required to turn them on and off. The items that I have, and they are generally available, are 5 volt. So this means you need some sort of a logic level shifter from, if you use a microcontroller like I do, which is 3.3 volt. And the other option that you can use is a MOSFET. So this acts like a switch. It will look kind of like this. And it does work. However, also for MOSFETs, they have a trigger voltage. So you have to get a logic level MOSFET so that you can actually trigger bigger loads. So for my next example, I will try to configure my breadboard, and I will use a MOSFET to drive a bigger LED strip. So let's pretend that this LED is actually a LED strip. So I cannot just turn it on by itself. So what I will do is I will put a ground, and I will want to add some sort of a switch, and I will use my MOSFET to act as such a switch between the ground and the LED. So it will look kind of like this. I take a wire from here into the MOSFET, I take a wire into the LED, and I will use the GPIO to turn the MOSFET on and off. And the LED also needs to be powered, obviously. So in this case, I will add voltage, and my LED strip is actually 12 volt. So the circuit that I'm planning to build is something like this. So LED, when the MOSFET is off, the LED will be off. However, when I turn the MOSFET on, the LED will be on. So let me take a couple of minutes to build up this circuit. All right, I have built the circuit. So let's connect the pin and run the program. And notice how the blinking is going on. And this is a 12 volt, so I can have a simple switch and control bigger devices. The circuit is quite complex, so I'll go back to using a simple LED for the next examples. Okay, I've put back the LED, and now let's talk about inputs. So before that, I will delete all these items. And I will keep a LED on PA0 for illustration purposes, but for now I will concentrate on input and output. And I will concentrate on inputs now. And inputs are basically when I want my microcontroller to see something, some value that comes externally. And this could be some sort of a sensor, or it could be a user pressing a button, or things like that. And the first example will be user pressing a button. And what my device can do is, if I put a wire somewhere, let's say PA2, it will be able to detect whether it's high or low. So the first idea that I could have is, let me get a simple switch, which looks like this. And in this case, I will say one end will be the ground, and the other end will be power, say 3.3 volts, because this is what my microcontroller supports. And I will put it like this. And I will connect this switch to my pin. So it looks kind of like this. This looks okay in theory, and it does work. However, this works when something is on or off. So let's say if I have a fan on, fan off, or if I have light switch on, light switch off. However, for many situations, users don't think of on off, but they think more on start on stop. So let's say I have a start a fan or a start a timer, and in this case I cannot have a start on start off, because that would be awkward. So I would rather have some sort of a push button. So I will erase this, and what generally we have is this kind of software push button. So when you push the button, the circuit is connected, and when the button is out, the circuit is disconnected. So let me connect this to the switch, and let's say I want my switch to be connected to ground whenever the switch is pulled. So I will take ground, I will place it here, and when the button is pushed, this circuit is 0, so it's connected to ground. However, what happens if the circuit is not pushed? So I would want to have the opposite. So in this case, I would want to have 3.3 volts when the button is not pushed. So I will take 3.3 volts, and if I connect this directly when the button will be pushed, I will have a short circuit between 3.3 and ground, and that will get hot, and also the value is not really well defined. So the other thing that I have to do is add some sort of a resistor. So I'll add a resistor here, and I'll connect it with wires like this. And this is my circuit. So in this case, let's say the button is not pushed. So if the button is not pushed, this part of the circuit is not connected. And the only part that is connected is this bit. So this means PA2 will read 3.3 volts. What happens if I push the button? If I push the button, this will be 0, and this is 3.3. So the resistor will act and will go from 3.3 to 0, but PA2 will read 0. So this is a simple pull-up configuration. Why is it called pull-up? It means that if I don't have nothing interacting with my circuit, the value is being pulled up to 3.3 volts, but if I push my button, it gets pulled back to ground. And there's also the reverse. Like I could put the ground up here, and I could put the 3.3 volts in the other side, and this would be a pull-down circuit. So if I have ground in the default state, and if I push the button, it will go back to 3.3 volts. So if you read a data sheet, I will close these images. If you look at the the datasheet and various configurations, you can actually see information. So for example, if I say inputs, it will say I have a pull down input or I have a pull up input, which uses the internal state of the MCU to actually provide these resistors that move the value to default 0 or default 1. And there's also floating input, which was the first example in which it would say, I don't know what the input will be, just trust whatever is on the line. And then some other external circuitry has to ensure that the value is either 0 and 1. And if you look at the data sheet, it will even give you information about what kind of a resistor is used for pull up and pull down. And in my case, it says it's around 40 kilo ohm, but there's a variability in there. So let's get started and attach some sort of button and see how this works. Connect A2 to one side, and I will the other side of the button I will connect to ground. So in this case I have A2, so let's go through the code and take both GPIO PA0 and PA2. I will explain my choice of PA2 instead of PA1 slightly later. So I want to return both of these, and they are returned as LED and a button. Now in my loop, what I want to do is whenever I read a button, so let's say if button is high, then I want the LED to be on, and if the button is low, I want the LED to be off. I put PA2 into push-pull, but into pull-up input because I want default to be on, and then when I push the button down, it will be off. And probably this will be reversed. I don't need a delay. This will be reversed because actually the default is high. So I will make Clippy happy by saying okay here. I know things will not fail, and cargo run. Notice that the LED is on because my default for the input is on. When I click the button, it will turn off. When I let it go, it turns on again. So I have input and output. Now next thing is this is an infinite loop that checks the LED. Very often we would like to have some sort of an interrupt. So I only want to get some sort of a notification whenever the input is changing. However, I do not want to continuously need to check the GPIO. And the way this is done is via interrupts. And if you read datasheet and documentation, it looks kind of like this. So there are several interrupts, external interrupts, and they are numbered 0, 1, 2, and so on. And you can see the 0 is multiplexing several pins at once. So all PA0 pins are on one interrupt, or PA1 are on another interrupt, and so on. And the other bit that's interesting is that at least the interrupt lines that we have groups 0 and 1 together, groups 2 and 3 together, and so on. And this is why I used PA2 as an input rather than PA1 because 0 and 1 are going together, and I use 0 for the LED, so I wanted a completely separate interrupt line for number 2. So let's go through it and see how we can set up these interrupts. So the first thing that I will do with interrupts is I want to enable the interrupt masks. So this is done using the external interrupts. So I will go through the peripherals and I will take the EXTI, and there are two things that I want, or well, there are several, but I need at least one, IMR, which is the interrupt mask. And I will modify this one. I don't need to read it, but I do need to write it. And because I'm going to the second interrupt line and PA2, I will access PA2 and I will set bit. So I modified this one, and this is mask enable. So I basically enable the interrupt. The other bit that I have is the following trigger set register. So whenever the value moves from 0 to 1, you could have a falling, which means from 1 it goes to 0, so it falls down, or you have the rising, so from 0 it goes up to 1. So this is the falling. What this effectively says is whenever there's a value moves from 1 to 0, so it's falling down, please create an interrupt for me. The other bit that I need to do is enable the actual interrupt lines, and this is not safe, so I have to use an unsafe block. And this is using the non-volatile interrupt configuration. So I do nvic unmask, and I have to pick which one to unmask. I have to import the correct package. I don't care about the STM32 F0 version, so I'll enable any of them. And then if I go back to main.rs, I define that I want to enable interrupt 2 and 3. The next part that I want to do is set up an interrupt handler, which is a method that will be called whenever the interrupt is actually triggered. And you can do this by using the interrupt macro. And the name of the function is important, so I have to name it exactly how the interrupt vector is expecting it. So this is exti23, and for now what I will do, I will just println. I will run this as is. I don't have the interrupt in scope. Let me add it. Now it should compile, and it will wait for the interrupt. What you'll notice is as soon as I click the button, it goes into an infinite loop of push detected, push detected. And the reason for this is that the interrupt is being set, but it is never cleared. So for me to clear it, at first I tried to just remove the pending, which I should be doing it anyway. However, this is insufficient. What happens is whenever this interrupt is being triggered, there's a register flag that says interrupt has been triggered, and unless you clear it, you will never be able to recover from this, because the interrupt will be kept on triggered and triggered again and again. So in order to avoid that, what I will do is I will share this peripheral. So I will want to have access of this EXTI both in main code, and I would like to have access to it in the interrupt handler so I can clear its status. And the other thing that I will do, I will also put a push counter so I can have something on the screen that displays the current status. So I will go in here, I will have a push count, and the next bit in my loop, what I would like to do is I would like to delay a little bit, and whenever the delay is finished, I would like to show my current push count. So I'll delete this. I have my push count, and I don't have the delay set. So let's reset it. Everything should be 0 right now because nobody changes the push count. However, the other thing that I have to put is make sure that I have access to this EXTI in my code. So now the interrupt handler has access to the peripheral, external interrupts. So I will use that. And in an interrupt-free version, what I will do is, first of all, I want to increase the push count. I'll get the current value of the push count, add 1, and then I set the new value. And then I will say, if I have some EXTI, please clear the, I guess, PR1 because it's a second line. Also, I want to make sure that I can use the deref call, so I will use core operations deref, which will make this this deref actually work. Now let's make Clippy happy and cargo build and cargo run. Now notice that whenever I click the button, the push count increases. The other thing that you notice is that the push count doesn't increase by 1 every click. And the reason for this is that the button is a physical device that sometimes connects, sometimes doesn't. So the values will kind of wiggle between 0 and 1 before settling down in either 1 or 0. So values will wiggle between 0 and 1 until they settle to their final value. So whenever I click the button, I may register more than 1 click, which is quite unfortunate. You have to handle this in software. It's called debouncing, and the general rule would be physically I am not able to push the button more than, let's say, once every millisecond or once every 50 milliseconds or something like that. So you put a timer or a timeout in software that says once you detect a push, do not consider a new push any value changes within the next X milliseconds, and that should work fine. I won't be implementing this in this example, but this is what you would do if you would implement, let's say, some sort of a game controller or a keyboard or anything that really cares about how many times you press a button. Like, it would be really unfortunate if I press an A here and that 5 A's show up on my keyboard. Great, so this is the input. This is a simple button input. Now, just as a simple example, again, another thing that you can do is not necessarily have a button as an input, but maybe you have some sort of a sensor. And in order to do that, I picked up this simple infrared PIR sensor. This is a motion sensor that uses body heat to detect if somebody is moving or not. And it gets powered by VCC and ground. Let me do that. All right, I made all the necessary connections. This time it's not a button, so I will not use this interrupt anymore. I will revert back to the code that was just checking the value in a loop. So the other thing is this will be pull up by default, but this will be fighting my sensor. So this is one of the cases that I want floating input. I want my sensor to control whether things are up or down. So let's cargo run. I rearranged the connectivity a bit. I needed a shared ground for the LED and the sensor. So now let's run, and I expect the LED to turn on. And now if I sit very, very still, because these sensors are very sensitive, eventually it should turn off, and then it will turn on once I move. Let's try that. Notice how even the slightest movement actually turns the LED on, and then after a while it will turn off. How long the on-off delay is generally configured by sensors. So if you have a more complex PIR sensor, something like this one, you can see it has all sorts of knobs that you can configure things, but this is more an integration. That was it. I hope this was interesting or helpful or both, and see you in the next video. Bye.